상식적으로 생각하는 외국이랑 별로 쓸거 없어요. 내 말이 그거예요.
Alright, let's start. Okay, so we are learning the last chapter in the big chapter 1, and so in this sub-chapter, we think of a matrix vector multiplication, which is ax as a function, right? So this basically sends this vector to another vector y, right? So so in this kind of a function representation, x is a part of or elements in this set of domain, and then y is belonging to this codomain or range. And, okay. And then we covered these two characteristics of linear transformation. So in the case of linear transformation, it has to satisfy these two equations, and then this can be represented as a single equation by combining both of them in this form. So as I mentioned last time, we first linearly combine the two vectors u and v, and then pass through our function t. And then the result becomes the same as the result from the linear combination of these two, and then these two are like function outputs. So we first pass each of these vectors into our function, and then we linearly combine those two outputs, and then the result becomes the same. Okay, so this is a key equation for a function to be a linear, or the transformation to be linear. Then we looked at this example. So I don't give any detailed information about the function t, but someone said these two specific mappings, so these two example mapping, which sends this vector 1, 0 into another vector 2, comma minus 1, and then 0, 1 into another vector, which happens to be the same as the input vector. And then interestingly, this is a simple but really important trick. So any vector in this domain, or two-dimensional vector, can be represented as a linear combination of these two basic or elementary vectors. Okay, so you understand this relationship, and then for any vector x, we can replace that into this guy, and then from from this relationship, we can change or convert this form into this form, which basically bring these linear combination coefficients out of the function or transformation t. And then we know each of these results, right? And then the result happens to be the linear combination of these outputs with the same linear combination coefficients. And then we know how to convert this guy into a matrix vector form. So we have two columns and their linear combinations, right? This can be rewritten as one single matrix, where we have these two columns in this matrix, and then those linear combination coefficients on the right. Okay, so Yeah, so this is another example. Let's see. So basically from this example, we can understand this theorem 10. So if T is a linear transformation, okay, and then its matrix that does this transformation can be represented in this form. So although this looks a little bit cryptic or complicated, but it's nothing but just concatenations of the columns from the result of the mapping each of these basic or elementary kind of vector. So yeah, this formal name of this guy is a unit vector or elementary vector. So this is something like this: 1, 0, 0, and then the second one is 0, 1, 0, and then 0, 0, 1. Yeah, and then we compute each of these outputs, and then we just put these results as a columns of A, and then magically you form this matrix A that does this linear transformation. Okay, that was the point of this, or the meaning of this theorem 10. And then specifically, this matrix A is called standard matrix. So this is not, an important name, but you should be able to know what this means, and then also have to answer the question about what is a standard matrix when certain clues or informations are given for your transformation. Okay. So we also looked at this example. So all we know is this guy, this relationship for any x in R2, and then we actively create these two vectors, which are our elementary vectors, and then this one becomes 0, 3, and this one becomes 3, 0, and 0, 3, and then the matrix is just a concatenation of those resulting columns. Okay. Okay, and then using this simple trick to form our matrix A for the linear transformation, we can do more interesting things. So this is about the rotation. So we learned from the high school about the rotation matrix. So when trying to rotate a certain point with the angle of theta, so for example, let's see. So if we have this point, and then we want to rotate it with like 120 degrees of an angle. Okay. In this case, we know the formula, right? So it's like cosine and sine and sine, cosine, and then 120, 120, 120, 120, right? And then minus is here, right? So this was already what we memorized in our high school. But we will learn a different way to come up with or obtain this matrix by just using the theorem that we learned. So this is basically using the same trick. So we use the input of this elementary matrix of 1, 0 or 0, 1. Okay, and then let's think about the resulting point or resulting vector after transforming these two guys with the, let's see, angle of, what's the name of it? Psi? Phi? Yeah, I think it's phi. Phi. Okay, let's call it phi. Even if it's wrong. But anyways, so okay, so in this case, so it's like a counterclockwise rotation, that's like this direction, right? And then 1, 0 becomes this point. So we rotate it with this amount of an angle, right? So we this triangle with the right angle. And then, yeah, we know the coordinates of this point is basically, yeah, so this is 1, right? So still, the result of this edge is 1. And so it's cosine phi and the sine phi. Okay, so the resulting vector from this guy through this transformation of rotating the with the angle phi becomes this guy. And then in the case of this guy, so this starts from here, right? And then the resulting vector is after the one after the rotation of the same angle. And then by using or by drawing this triangle in the same way, we cannot easily come up with or obtain the resulting vector. But here, yeah, we have a minus sign here because this result, I mean this length is in this part of x equals minus, x is less than 0. So we got these two vectors as a result of mapping each of these two elementary vectors. And then we can just simply concatenate those columns. So this guy came from here, and this guy came from here. So that becomes our entire matrix A. Okay. Okay, so yeah, we can use the same trick for all the other or many other transformations. So in this case, yeah, there are like 5 examples here. So in this case, we are basically handling this reflection, but here we are reflecting through the x-axis. So in this case, so those blue and red vectors are the result of the vectors of transforming 1, 0 and 0, 1. So in the case of reflection through x-axis, so for any point x, so we obtain this guy because we are reflecting it through this x-axis, right? So let's think about the 1, 0 case. So this is 1, 0, and then this will stay the same in terms of the result. So the same result will be put here. But in the case of 0, 1, then it will become 0, minus 1. Okay? So that way we obtain this guy, right? So this guy is the same, and yeah, let's look at this. So it's a reflection through y equals x. Okay. So in this case, if it was a comma b, and then what is the result in this case? B comma a, right? Okay, so here, yeah, we use the same trick. So this is a 1, 0, right? And then we know it is becoming this guy of 0, 1. Okay, so we get this, right? And in this case, this goes back to this exact point of 1, 0. Okay, so that's how we obtain this matrix that does this reflection through this y equals x. Okay. Yeah, these are all easy. But let's think about one more thing here. I mean, so in this case, still we have to require the assumption that all these transformations are linear, right? So let's see. So basically, the reason why we can do this trick is based on this exact theorem, theorem 10, right? And then in this case of theorem 10, the basic assumption is this guy is linear transformation, okay? And then we basically used this guy, right? So we basically used this guy, which is one single property of the linear transformation, to obtain this kind of relationships, right? And so, in this case, if we think a little bit deeply about these examples, and then we have to have an assumption that each of these transformations are linear, right? So, and then, in order to prove or verify each of these are a linear transformation, we can actually verify the two basic properties that the linear transformation has to satisfy. So, what was it? So, in this case, let's see. So, we think of these 2 points, okay? And then, let's see, at this point, maybe this, okay? And then their resulting vector after summing these two up will become this guy, okay? So we have to think, we have to verify whether it is true, like that the function transformation of this point is this guy, right? So we have to see if this guy is the same as the summation of the function transformation of these two. So this guy becomes here. See, this guy becomes here, and then we have to verify the summation of the function outputs are the same as the function transformation of the summation of these two vectors, right? So that's how we can verify each of these are linear transformation. Although we have to verify one more thing, which is a scalar multiple, right? So in that case, let's use another color. So we have points here, and then the resulting point in here from this transformation. And then we just a scalar multiple with maybe 2.5 times. Okay, so the length is 1, and then this guy's length is 2.5. Okay, and then the transformation of this point is here, and then we have to verify this guy is the same as the function transformation. I mean the scalar multiple of the function transformation of the original point. Okay. So you know what I'm currently doing, right? So I'm basically trying to verify those two. The first and the second properties that we have to satisfy for the linear transformation. In the case of each of these functions. So okay. Okay, let's look at a few more examples. Okay, in this case, it's a horizontal contraction or expansion. So this is basically doing. So here, let's consider x comma y. Okay, in this case, this function is doing horizontal contraction. So this horizontal coordinates gets gets smaller or expanded or bigger. So let's call that the factor as maybe k, and then this guy becomes kx comma y, right? Because we we did a scalar multiple only on this x coordinate. Okay, so if k is, for example, 2, then this point will be 1 and 2 here, but with the still same y value. Okay, so this is the transformation from this function. Okay, so this is still the same. So in the case of 1 comma 0, it is transformed into k comma 0. So this is comma, and then 0 comma 1. It will become just 0 comma 1, because we don't do anything along the y-axis. So by concatenating each of these as columns, k comma 0 and 1 comma 0 comma 1, then we obtain this matrix, right? We can do the same thing on the vertical contraction and expansion, and this one is called projection. Projection, yeah. So this is really an important concept. Although this in this specific example, it's really simple one, but we will, learn maybe in a month or so. Yeah, we will learn how to project those points into some subspace or our span, for example. Yeah, so this is an interesting fact. So we learned. So we learned about like two different situations. In the case of linear linear equation or matrix equation or linear systems or whatever. So let's see. Yeah, let's change it into B. So we were first considering whether B is inside of our span or outside of the span, which can be represented as the columns of A, right? But in case B is outside of our span, we can actually do some trick to make that guy inside of our span. Okay? So this is something like this. So suppose our span is this kind of a line, and then so in this case, let's see, 2, 1, for example. And then let's see. In the case of linear system, so suppose we only have just one single column, and then in our original matrix will become just 1, 2, right? And then since we only have one column, we only have one variable in x part. So the dimension of the x here, because these are the linear combination coefficients of these columns, but we only have one column, and so we only have just a single value in x part, right? And then suppose our vector b here, and then in here we know the span of this vector is this guy, right? All the points along this line through the origin and 2, 1. Yeah, it should be 2, 1, right? Okay, and then suppose we have, I gave you B as like 2, 2, okay? 2, 2. Okay, I gave you B here. So clearly B is outside of the span of this column vector that we have in A, right? So in this case, we clearly see that there is no solution. And in this case, if we construct the augmented matrix, this guy, and then we will clearly see like a 0, 0, 0 and B. Right? And so here, this is A part and this is B part. Okay? And then in this case, we will see 0 and B or some non-zero value. Okay, but in this case, even though the solution, exact solution may not exist, but here, we can do some trick that projects this point to the closest point inside of our span. Okay, so that way, we can always obtain the approximate vector b. Okay, so that this approximated version of the b is inside of our span, and then we can now get the solution for any vector b by just approximating b into the closest point in our span. Okay? So this is also called a projection because we are projecting this guy into this this line, right? But what if we have like another columns in A, and then our span of the columns of A will 왜 프로젝션 하냐고요? 누군가가 솔루션을 달라고 이야기를 해서 그러니까 그 솔루션이 그러니까 없다라고 그냥 간단하게 얘기할 수 있는데 이제 누군가가 이제 솔루션이 이제 정확하진 않아도 근사적인 솔루션. 그러니까 정확한 솔루션을 구할 수 없어도 그냥 네가 할 수 있는 최선을 다해서 한번 가장 비슷한 솔루션을 한번 구해봐라. 라는 문제를 줄 수가 있어요. 그리고 이 문제가 생각보다 굉장히 여러 군데에서 굉장히 많이 쓰이는 그런 어떤 거고요. 그냥 이거 뭐 재미없는 이제 소형대수는 우리가 하고 있는데 뭐 요즘 들어봤던 뭐 알파고 왜 되게 좋아하는데 알파고? 알파고 왜 이렇게 좋아하지? 즉 알파고 뭐 그런 뭐 흔히 얘기하는 딥러닝, and then 뭐 그냥 다른 어떤 여타의 머신러닝 알고리즘들이 뭐 이런 식의 것들로 많이 풀려요. 그러니까 B가 기본적으로는 스팬에 없는 형태로 이제 포뮬레이션이 많이 일어나고 거기서 이제 approximate 솔루션이 어떻게 보면은 우리가 할 수 있는 가장 그 베스트한 솔루션을 얻을 수가 있는 거고 그게 이제 이런저런 재미있는 일들을 또 많이 하고 또 이제 약간은 좀 이제 인투이티브 하진 않지만 이게 좀 뭐라 해야 되나 카운터 인투이티브 하지만 그러니까 저희 우리의 좀 생각에 좀 반대될 수 있지만 오히려 정확한 솔루션을 만드는 것보다 좀 정확하지 않은 솔루션을 만드는 게 나중을 위해서는 더 좋을 수도 있어요. 그러니까 알파고가 바둑을 둘 때 정확하게 맞추면 이세돌을 못 이기는데 그거를 좀 일부러 부정확한 솔루션을 얻어 놓으면 그걸로 이제 이세돌을 이길 수가 있어요. Okay, so the question was, what is the situation or when should we do this kind of approximation, even when we have no solutions? Okay, so there are many practical reasons or needs, and many of these machine learning and deep learning and even those AlphaGo things are actually utilizing the exact same tricks, okay, to actually obtain the better solution. Yeah, so. Yeah, although it sounds a little silly or counterintuitive, this kind of approximate solution may work much better than the exact solution. So people sometimes intentionally obtain the approximate version of the solution instead of the, even though they can obtain the exact solution sometimes. Okay, so this is about the projection, and then we will learn about the more interesting cases for these projections. But in this specific case, so we are learning very simple case of projection onto just a single x-axis. So whatever point x comma y, they are projected along the x-axis, which is x comma 0. Right? Okay, and then okay. So still the same trick applies. 1, 0 becomes 1, 0 because this guy is 1, 0. They don't move at all, and 0, 1 will become 0, 0. Right. So in this case, we have point here, and then they are projected onto 0, 0, which is the origin. Okay, and then 1, 0 is written in the column form, right? Okay. Okay, finally, we reached this onto and one-to-one, and then I believe I explained well about this concept of one-to-one and then onto. So let's read through the formal definition of this onto and one-to-one. Okay. So onto means, so if you recall our range, okay, and this kind of function mapping, so our range should be the same as our codomain, which means every element in our codomain should get hit at least once, right, from some vector or some elements in our domain, right? Okay, so that thing can be stated in this form. So NAB, because this guy is our codomain, right? So we pick up or choose any vector B belonging to our codomain, okay? So that should be included in the range as well. And then at the same time, it can be restated in this form. So any vector B is an image of some vector x, okay? But there can be multiple vectors that shoots the arrow to the same guy, right? So it's completely fine, but at least any entries or any vector B in our codomain should get hit at least once, right? And then it means it is the image of at least one element x in our domain, right? So this is domain. In this case, it's codomain. And then where is a range? Range is a set of all the images, right? All the function values that gets actually hit by the arrow, right? So image is actually some elements in the range, right? Okay, so this is onto. And then let's look at this figure. So this is something like this. So this entire three-dimensional space is our codomain. Okay. So although it's stretching out unlimitedly to all the directions, but in order to just easily visualize them or draw them, we think of this just a cube. Okay. And then unfortunately, our range or the span of the columns of A is not covering the entire space. So it's only just a plane out of this entire three-dimensional space. In that case, it's definitely not, it's not onto because we didn't cover the entire space, right? So that's, yeah, this is one example where this transformation is not onto because we didn't cover the entire space. We only covered this plane out of this three-dimensional space. Okay, this is not a good figure, but yeah, this represents the case where the range and the codomain becomes exactly the same. So, so this plane is a codomain as well as the range. Okay. Okay, and then in the case of one-to-one, we don't consider whether we cover the entire space up or not. Right? We only focus on our range, the elements in our range. So again, we do not care how small our range is. So our range could be just a single point. So yeah. Let's see. Yeah, although this looks, let's see, yeah, okay. Okay, let's think about this kind of transformation. This looks really trivial. So this is composed of just one single vector, which is just a zero vector. Okay. So in this case, so what is the range? What is the range? What is the set of all the possible elements for this y vector? It only contains this guy, 0, 0. So in this case, our range is really small. This contains only one point. Okay, but still, we still have a chance, or we still have a hope that this function can be one-to-one. Okay, because we only care about the ranges, how small, regardless of how small it is. Okay, okay, and then it is. Yeah, let's look at this definition. So here we consider any B in Rn, so we still consider all the elements in our codomain, and then yeah, still strangely it is saying this is an image. Okay, this is an image of at most 1x. Okay, so it means among our codomain, some entries gets hit by only 1x, or some other entries gets no hit. Okay? So that's the meaning of this at most. Right? So again, in our codomain, all the elements outside of our range gets no hit. Okay? So they don't get hit by any arrows. Right? So it means that's the meaning that this point is outside of our range. Right? So still that can be written as, so that vector B is an image of at most 1x, which contains no x as well. Right? So at most is like this guy, equal to 1 or less than 1. Right? But in the case of points or elements inside of our span or inside of our range, so that gets hit by still at most one entry, which means in case they get hit, they can only get hit only once. Okay? So that is the definition of one-to-one. So yeah, in this case, yeah. So clearly this is not onto because the range is not the same as codomain. And then for each entry in our range, they get hit by multiple elements in our domain. So in this case, this is not onto. And then in this case, where each point in our range gets hit exactly once, and then this is called one-to-one. Okay, and then yeah, if we recall what we learned last time, this one-to-one thing is related to which variable? Yeah, what or which variable was related to or determined this one-to-one thing? Yeah, free variable. So this is simply like if we have a free variable and then this is not one-to-one, and then if we have no free variable and then it gives a exact one-to-one mapping. Okay. So free variable was also related to this guy, homogeneous linear system. Okay. So in this case, this guy x can have either like unique solution of all zero vector or some other vectors, which we call non-trivial solutions, right? And then this non-trivial solution were determined by our free variable, right? And then those multiple solutions to get mapped to the origin, which is also a single point. Okay? So origin or this all zero vector is always inside of our span for whatever transformation AX. So regardless of what A is, this zero vector is always inside of our span. Right? And then for this specific entry, we should always have just a single mapping, okay, single arrows to get mapped to this zero vector. 여기요? 아니면 이거요? 네. 요거? 네.
저거는 원투원이 아니잖아요.
이거요? 이거 원투원일까요? 아닐까요?
모르시죠.
네? 저 원투원일까요? 아닐까요? 네?
도메인에 따라.
도메인에 따라? 도메인은 뭐 R이죠, 뭐 R. 1초. 네. 왜 아니라고 생각해요? 네? 다 제로제로로 하니까, 네. 그렇죠. 네. X가 여기서는 아무거나 돼도 다 0, 0로 가죠. 그죠? 그러니까 이거는 원투원 그냥 개념을 생각을 해보면 이 0,0이라고 하는 우리의 레인지 아니면 스팬, 요놈들의 스팬 안에 있는 어떤 한 엘리멘트, 요놈에 대해서도 화살이 한 번만 가야 되는데 화살이 지금 여러 개가 지금 얘로 쏘고 있거든요. 실제로는 모든 애들이 다 얘로 쏘고 있죠, 화살을. 그죠? 네. 그렇기 때문에 이거는 뭐 원투원 그냥 정의만 생각해봐도 이건 아니에요. 네. 그죠? 이거는 그리고 또 어떻게 볼 수가 있냐면, 자, 근데 원투원. Okay, so basically this one is clearly not one-to-one because for any value x, it is always mapped to this exact same y or the resulting vector, right? So that way, from the meaning of this one-to-one, we can easily see that this one is not a one-to-one. Okay, and then we thought about this one-to-one thing in terms of a free variable, right? So in this case, it means it should have some free variable. So, do we have a free variable or not? Here. 네? 질문이요? 지금? 그래요. 저 원투원은 기본적으로 free variable의 유무와 상관이 있죠, 직접적으로. 그죠? 근데 free variable이 있어야 원투원이 아니고 free variable이 없으면 원투원이라고 해요. 그럼 이 경우는 원투원이 아니라는 걸 우리가 이제 뭐 쉽게 이제 알 수가 있었는데, 그럼 이 경우는 프리 베리어블이 있어야 되는 거잖아요. 네? 그럼 프리 베리어블이 있는 건가요, 그래서? Yeah, so yeah, this case, yeah, has the free variable as well. Yeah. Yeah, so what was a free variable? So the columns or the variables that does not contain any pivots, right? So yeah, let's try to create or change this guy into like a staircase shape. But we have nothing to do to make this guy as a staircase shape. So stair has ended already here, right? And then at the same time, this all zero column vector does not contain any pivots, right? So that still makes us happy because we can still call that as a free variable because it does not contain any pivots, right? So yeah, we can call that as a free variable. And so yeah, this is not one-to-one, okay? So in this specific case, yeah, it's not one-to-one. Okay? Okay, and then yeah. So this is another kind of interpretation about this. So what was a free variable and what was basic variable, which is like opposite of a free variable. So as we add one vector at a time, so if one particular vector increases our span, that was actually the basic variable. And then in case some vector is not increasing our span, so it's part of the span of the previous vectors. And then that corresponds to the case where this vector is not a basic variable, or, yeah, in other words, this vector is a free variable in that case. Right? So in the case of zero vector, so zero vector does not increase our span, right? Suppose we have two vectors and we added zero vectors, right? And then this zero vector doesn't increase our span. So that way it's still a free variable, okay? And then, yeah, this free variable was also related to kind of linearly dependent or linearly independent. So in case we have a free variable, it is the same as the case where these vectors or column vectors in A are linearly dependent, right? So linearly dependent was the same as the case where we have some free variables in our A, right? So free variable is the same as linearly dependent. Okay, and then we also learned that zero vector. So if we see zero vector in our vector set, and then we can immediately say that this set is linearly dependent, right? So linearly dependent means we have a free variable, okay? Yeah. And then zero vector is always makes our set of vectors as linearly dependent, okay? So that works as a free variable, okay? Okay. Any other questions here? Okay, then yeah, since we have this kind of understanding from many different angles about these, so those two theorems that should be easy. So we consider this a linear transformation, and then T is 1-to-1 if and only if this Tx equals 0 has only trivial solution. Okay, and then in the case of linear transformation, this is so T of x is written in this form, right? And then again, this A corresponding to this linear transformation T was called, what was it? Standard matrix, right? For this transformation. This is just an idiom or just a term. Okay, so in this case, if this guy has only the trivial solution, which means our matrix A has no free variable, and that is actually exactly the same as T is 1-to-1. Okay, so that's already what we already know. And then theorem 12 is saying, Okay, T maps this guy. So here, onto. Okay, so it is saying T is onto. So although this one was used as a preposition, so we should really catch this mapping is onto. So it's not like a mapping Rn to Rm. Right? So this means specifically this mapping is onto. Right? 이게 무슨 소리인지 알겠죠? 그러니까 여기 전치사로 쓰였지만 이거가 그냥 RM으로 그냥 왜 표현한다는 게 아니라 이거는 onto, 이게 전사인가 뭐 이런 뭐 한글로 있던데 하여튼 onto란 뜻이에요. 이거 놓치면 안 돼요. 이거 왜냐면 작년에 시험 봤던 학생 중에 이게 그냥 onto가 여기 있는데 이 onto가 중요한 단어인데 이게 그냥 RN에서 RM으로 그냥 매핑하는 거다라고만 이해를 해갖고 네, 틀린 학생도 있고 그랬었어요. 네. Okay. Yeah, so onto is the same or equivalent to the case where the columns of A span Rm, which means the span of these columns of A, yeah, is covering up the entire space, right? And then this one, yeah, was the same as this theorem 4, right? Oops. Okay. And then T is 1-to-1. Yeah, this guy is equivalent to the case where the columns of A are linearly independent. So it only has a trivial solution, means we have no free variable, and then this one is the same as linearly independent one. Right? Okay, so it says check the proof in the textbook. Okay. Okay, so here in this example, we have to answer the question about whether this mapping T defined by the matrix A is 1-to-1 or not. Okay, so 1-to-1. So we have to identify some free variable. So whether we have a free variable or not. Okay? So how can we identify whether we have a free variable or not? Okay, this one is already echelon form. Okay, so here, do we have a free variable or not? Yes, right? This guy, right? Because we have a pivots. So variable 1, 2, 4 are our basic variable. That actually increases our span, right? But in the case of this, the third variable is not our basic variable. So that way we have a free variable, and thus these ones are all linearly dependent, right? So that is actually the same thing, and then that is also the same as the case where T is not 1-to-1, right? So the answer is clearly no, right?
원투는 프리밸류를 6으로 판단할 수 있잖아요.
네.
원투는 그걸로 판단할 수 없어요.
온투는요, 우리의 컬럼들이 공역 아니면 이 RM인가요? RN. 나도 헷갈리네. M이에요, N이에요, 이거. 자, 네, 보통 공역을 이제 RM이라고 한다면, RM이 그 Y 벡터들이 살고 있는 스페이스가 RM이에요. 전체 스페이스, M 디멘전 스페이스 전체. 그거를 다 커버를 하고 있느냐, 안 하고 있느냐. 우리의 스팬. 혹은 우리 함수값들이죠. 함수값이 정확하게 이제 영어로 이미지라는 뜻이고요. 이미지들을 다 모아놓은 게, 그러니까 함수값이, 실제로 함수값이 되는 애들을 다 모아놓은 걸 우리가 치역이라고 하잖아요. 그 치역과 공역이 똑같은 게 onto예요. onto.
그러니까 그 프리밸류가 물론은 판단할 수 없는 것 같아요.
네, 그걸 판단할 수 없고,
그 전체 그 스타일을 덮느냐
안 덮느냐를 판단할 수 있고요. 그 덮느냐, 안 덮느냐는 그 theorem 4에서 우리가 열심히 배웠던 거. 네. 그 다음에 뭐 이렇게 하나하나 애들을 했을 때, 이제 다 덮을 수 있냐 없냐. Okay, and then there is another example where the transformation is formed in this way. Okay, so So we have a comma here. So we should be able to construct a matrix from this example. So how? So what is our variable vector? x1 and x2. Okay? And then from here, let's construct our matrix A from this transformation T. Now this one is really important, although this one is simple. So what should the matrix look like here? 3, 1, 1 or 5? 1, right? Because they are mixing up with the x2, right? So this guy is linearly combined or inner product with this guy. 3, 1 and 5, 7 and 1, 3, right? And then we have these two column vectors, right? Okay, and then yeah, from this example, let me ask one question. So, what is T of 1, 0? Okay, 3, 5, 1. So, if you actually did some inner product by just plug this guy into here, and then you guys didn't do very well, okay, you should be able to answer right away this question, because 1, 0, so from this kind of standard matrix thing, so the first column from our matrix should be the answer or output of this 1, 0, okay? And 0, 1 output of this guy is the same as this guy, right? Uh-oh, yeah, we got the answer here. Okay, anyways, so from here, let's see. We can verify whether this guy is 1-to-1 or not. 1-to-1, let's see. 1-to-1 was related about the free variable. And this guy will have no free variable after making them into a staircase thing. And so this guy is 1-to-1. Okay? And then can we, yeah, so in this case, can this mapping, or is this mapping onto?
No.
No? Who said no? Where? 네, 그렇죠. 야, 한 일주일 전에 얘기했던 거를 잘 기억하고 있네요. 일주일 전이었나? 네. 그렇죠. 그때도 얘기했듯이 우리의 저기 그 정역은 R2고 공역은 R3예요. 그죠? 그러니까 이거는 R2가 훨씬 더 작잖아요. 그죠? 거기서 화살을 다 한 번씩 쏘면 저쪽 R3를 다 커버를 할 수가 없어요. 그죠? 그리고 또 그건 진짜 그럴까? 그것도 뭐 생각을 한번 해볼 수가 있는데 이렇게 생각을 해볼 수가 있어요. 그때도 얘기했듯이 이제 R2는 하나의 평면이고 R3는 이제 이 평면이 되게 여러 개 있잖아요. 그래서 저쪽에 있는 뭐 어떤 건지 모르지만 한 평면을 우리가 커버를 할 수 있지만 그 평면이 무수히 많은 거죠. 그러니까 커버를 못하는 부분이 넘쳐나는 거죠. 네, 그렇기 때문에 이건 onto가 안 되고. Okay, so simply because R3 is a much larger space than R2, so yeah, we can easily say that this one cannot be onto. Okay? And then also let's also apply what we learned in the previous slides to this situation. Okay? So we learned that this onto thing is the same as theorem 4, which determines whether we cover the entire space up, right? And then that was the same as we have all the pivots in the each rows of A, right? So in this case, we basically have this 3x2 matrix, right? So in this case, we are living in the three-dimensional space. So all the y's or all the column vectors in A are living in this three-dimensional space, but we only have two vectors. Okay? So even if we add these two vectors, this can only form just a plane, right? It cannot cover the three-dimensional space, right? And also, that is the same as we can only have two pivots here, right? So that pivots, let's say, okay, the red color. Okay, suppose our staircase shape or reduced echelon form is formed in this manner, and then we have pivots, right? So in this case, by just applying the theorem 4, it is saying we should have a pivot at each column. So column here and here, but not here. So it's not satisfying the theorem 4, and thus this guy is not onto. Okay. Okay. So this is probably the last slide. Okay, so about the onto and one-to-one, this is saying something about the pivot. Okay, and then interestingly, it's like a tricking or playing with the words. But in the case of an onto, the matrix A has a pivot in every row. Okay, that is the same as onto. And then in the case of one-to-one, pivot should be in every column of A. So it's really like the difference in terms of row or column, right? Yeah, but it's not something that you should memorize. You already understand deeply about it, because this guy is exactly the theorem 4 that I just described in the previous page of this guy, right? We should have a pivot in every row. So that's the condition or the requirement for onto, right? And then in the case of this guy, pivot in every column means all the variables are free variable, which means there is no free variable. All the variables are our basic variable because every column contains a pivot. So that means we have no free variable, right? So that is the same as on one-to-one. So we already learned it, right? So although, you have some kind of so you get tempted to memorize these things, but you don't really memorize these. Once you have a good understanding about all the things that we learned this lecture. Okay, so that is it for chapter 1.9. Then let's look at chapter 2.1, which is matrix algebra. Okay. So we will learn about the basic notations. So our matrix A is m by n, which means we have m rows and n columns. Okay. And then small lowercase a of ij is this guy, which is just a scalar. Okay. So I'm using just a plain font, not a bold font, right? And also lowercase, which means a scalar. But this specifies the positions, i's row and j's column. Okay. And then we think of each columns of A, right? And that column is corresponding to, or called this A1 and AN, since we have n column. And here, please note that these A's are in bold font. So that way they are vectors. Okay. And then simply using these column vector notations of A1 through AN, we can represent the matrix A in this form. Okay. And then this diagonal entry. This diagonal entry is these guys, A11, A22, and so on. Okay, so these are our diagonal entries. Okay, A11, A22, A33, and so on. Okay, and they form the main diagonal of A. Okay, that's just a term. Okay, then this diagonal matrix. Okay, so this is a square matrix. Square matrix which has the same size of column rows and columns. And then also this diagonal matrix should have all 0 for non-diagonal parts. So simply like the one example of 3 by 3 diagonal matrix is something like this: 3, 5, 1, 0, 0, 0, 0, 0, 0. Okay. So this is one example of diagonal matrix where we only see non-zeros along the diagonal, but all zeros along the off-diagonal parts. And then, those are echelon form and reduced echelon form. So reduced echelon form is actually the process of converting or changing your matrix A into like into a little bit of a diagonal form. Okay? But you cannot always convert your matrix into diagonal matrix, right? So so in the case of reduced echelon form, these diagonal parts should be all ones, right? Because we do this kind of scaling. But in case we have no free variable, we can make this kind of a diagonal matrix. But if we have a free variable and then this gets off diagonal part, right? So this one was diagonal, but this guy is not diagonal anymore, right? But anyways, conceptually, changing your matrix into reduced echelon form can be viewed as like changing your matrix into more like a diagonal form or diagonal matrix. Okay, and that diagonal matrix makes it easy to solve the linear system. And then n by n identity matrix is like 1, 1, 1. Okay, so this is one example of identity matrix, which is I3, right? Because I3, right? Because it's in a 3-dimensional or a 3 by 3 matrix. Okay. Okay. So just like a zero vector, we can define this zero matrix where all the entries are 0. And then if two matrices are equal, so suppose I give you like these kind of 3 by 2 matrices. I mean 3 by 2 matrices, so A and B. So A and B are equal in case each of these entries are exactly the same. So all the entries, all the corresponding entries should be the same in case the two equal matrices. Okay? And then what if these two matrices are not having the same size? So what if our matrix A is 3 by 2 and then this guy is this 2 by 2? Okay? So in this case, we cannot even say whether they are equal or not, right? Because we only think of the same size of matrix when thinking about the equality between these two matrices. And similarly, we can define the sum of these two matrices. So sum is simply just adding the corresponding entries up, right? And also in this case, also these two matrices of A and B should have the same size. So that's how we can at least define the summation of these two matrices. Okay, so in this case, A and C. So the question is to compute A plus C. So it's undefined or not defined, which is really obvious because they have a different size. So for these kind of entries, we have no entries anymore to add these two guys, right? Okay, and then there is also another concept of this scalar multiple. So R is scalar and A is our matrix. So this is also the simple. So 2 times 1, 2, 3, 4. Yeah, just like a scalar multiple of vectors, it is just a 2, 4, 6, 8, right? Okay, and then now finally sum theorem, okay, theorem 1, but it's really trivial. This it holds true, so this is true when changing the order of the summation, which is called 뭐죠 이거? 교환 법칙? 네. Commutative law, right? Commutative law. Commuting. What's the meaning of commuting? Or commute? Commute가 뭐죠? 뜻이? 네, 뭐라고요? 네? 뭐라고 했어요? 출근하다 맞는데? 네. 출근하다. 네. 뭐 통학하다, 통근하다 이거를 커뮤트라고 하죠. 네. 그래서 집이 나는 너무 멀어. 네. 통학하기 너무 멀어. My commuting time is so long. 뭐 이렇게 얘기하는데 commuting time. 그러니까 통근 혹은 통학 시간을 의미를 해요. 오케이. Okay, there are a bunch of more items in theorem 1. This is the same, and this is also the same. So here, okay, so 0 here is actually a matrix having the same size as that of A, right? So A and this 0 thing should have the same size to be able to write this equation. And then scalar multiple can be distributed in this form. And the two scalar multiples can be also distributed in this different way. Okay. Okay. Okay, so matrix multiplication. So here in this case, we think of the two matrix multiplication with one vector here. Okay. So in this case, using the theorem 1, it can be either computed in this form. So we first compute the matrix multiplication, and then the vector multiplication with x. That is the same as this guy, right? But here the meaning is a little bit different. And then, yeah, basically like bx, for example. So this can be viewed as the transformation T, which has the matrix B, right? And then in terms of this transformation sense, or if we view this kind of a thing, matrix vector multiplication as some transformation, so we first send the vector x to another vector using this matrix B. Then this is, for example, y vector. Okay, and then after that, we also compute the matrix multiplication with A. So we can think of another transformation of AY, for example. So this one is T1 and this one is T2, and then this one is T1 and this one is T2, and then this guy is sent further to another vector by the matrix A. So this is the final result. Okay. So that is corresponding to this representation. We first apply x. We first apply this transformation B with the x, and then the resulting vector gets multiplied with the another matrix A. Okay, and then that thing is the same as this guy. So the interpretation of this guy is slightly different. So in this case, we first compute this A times B. So overall, this can be viewed as maybe another transformation T3. Okay, so we do just a one-time transformation instead of two-step kind of process. Just one step of a transformation, which is defined as A times B. Okay? And then using this one-time transformation, we can send this vector x directly to, for example, z. So let's redefine this guy as y and this guy as z. Okay? Okay, so from this relationship, what do we do with these? Okay, so we can think about the meanings of this one-step transformation using some columns and rows of A's and B's, A and B. Okay, and so in order to learn or study those relationships, let's just define the columns of B as B1 through BP. Okay, and then let's leave the matrix A just as it is. Okay, and then in terms of the size, suppose that the size of A is m by n and B is n by p. So these two numbers should be the same, right? So that we can define the matrix multiplication of A and B. Okay? And then in the case of n by p matrix B, that has p number of columns, right? Okay, so yeah, we will do a little bit of a very simple trick. Okay, so yeah, in the case of A times X, so let's first compute Bx. Okay, Bx is B has these columns, like for example 4 columns: B1, B2, B3, and B4. And then our X should have 4 different entries because they are working as linear combination coefficients. And then in terms of a kind of a vector equation, so they can be represented in this form: linear combinations of these vectors using the linear combination coefficient of x1 through xp, which came from here. Right? And then by just applying A matrix further, so A times this guy and A times this guy, okay? And then we can switch the order between the scalar and this matrix, and then yeah, we get this representation, right? And then let's think about this A times B1 and also A times BP. Okay. So suppose this one was 3 by 4. Okay. And then A should have maybe 2 by 3. Yeah, this can be one example of A. So we have whatever number of rows, but we certainly should have like 3 columns in A. So that's how we can define the matrix multiplication between A and B, because B has 3 rows, right? And then this entire A thing times each of these vectors, B1 through B4, right? A times B1, okay? So now this guy can be viewed as kind of another representation of like AX, right? So B1, so here each of these B works as a linear combination coefficient that like mix and matches or linearly combines the columns in A. Okay, so overall A times B1 is forming 1 column, right? So we obtain another column, and then overall by just treating each of these ones as one single column, and then we can think about this one matrix, which is represented as a linear combination of these columns using those linear combination coefficients. Okay? So entire transformation can be defined in this form. So this guy can be viewed as just a one-step transformation, A times B of X times X. Okay? So this is a one-time transformation, and that corresponding matrix is represented in this form. Okay, so let's wrap it up today, and then continue this Thursday. Okay? 네, 수고했어요.
영어로 알아야 돼. 어디지? 직급 아니야?
그 중간고사 범위는 챕터 1만 나죠?
아, 중앙고사 보면 네, 챕터 1.
알겠습니다. 감사합니다.
네. 네. 오늘이요?